Could you let me share the screen now?
You can share the screen. Yeah, you should.
It says host.
Okay. Yeah. Okay.
Host disabled participant screen sharing.
Okay. So is that okay? Can you share now? Great. This looks fantastic. Yeah. Yeah, you can go to slideshow. It's on the yeah, there you go. Slideshow.
Okay, is that working now?
Yes, looks very good. Yeah, thank you very much.
Okay, well, thank you, Peng Chen, for the kind introduction, and I'm very glad to give a talk today about strontium ruthenate. So here's a list of my collaborators. Yeah, so the main person doing the work actually was with Chris Lester and Richard Waite from Bristol, and the crystals we used were grown by Robin Perry in collaboration with Chris, and we've done experiments at ISIS, and also some of the work is done at the RLL. Okay. Okay, so let me just move on quickly then to what I'd like to talk about. So quantum criticality and quantum critical points is quite a big theme in condensed matter physics at the moment. As you know, you've got many materials, including things like high temperature superconductors and the pnictides, where we think that there's a quantum critical point and quantum criticality, and that can be used as a phenomenology to understand the properties of a system. So if we just take a step back a bit and think about how we look for quantum critical points in a general way, I've illustrated two types of quantum critical point here on the top. One where you have an ordered phase and you have a control parameter and you suppress the ordered phase and you get a quantum critical region. Or another one perhaps where you don't really see the much of the ordered phase. You just somehow have a control parameter that takes you near an ordered phase or a small region of ordered phase, and then you have a region like this and sort of a non-ordered region on both sides. Okay, so one way to look for this quantum critical region is to look at the entropy of the system, and I've illustrated that here. Of course, the entropy of the system goes to zero at zero temperature. So when you scan across at zero temperature, you won't see a change in the entropy as you go through the quantum critical point. But if you do it at finite temperature and cut through, you'll see a peak in the entropy as a function of your control parameter. And that can be used to sort of find out where your quantum critical point is. So you could take the entropy divided by temperature or even the low temperature specific heat. So today I'd like to talk about how we can connect the entropy and the specific heat, i.e. the thermal properties, to the excitations in a model material for doing that, which is strontium ruthenate. And I'll show you in a minute that strontium ruthenate is nice to look at this because we have an ordered phase at low temperatures below about 1 Kelvin, which is a very small region of ordered phase. And then we have a big region above where the entropy and heat capacity have been measured. And we're able to actually go along at very low temperatures and see the excitations in the system and connect them to the entropy in a phenomenological model, which I'd like to tell you about. And as I said at the beginning, you can also think about other systems in this way. So here's a Cuprates actually. This is lanthanum strontium copper oxide with europium and neodymium in, and a paper with from Louis Taillefer and collaborators, where they've measured the low temperature specific heat, and they see this peak in the specific heat at low temperatures, indicating possibly something like a quantum critical point, which I mentioned before. So let me tell you a bit about strontium muthenate. So the strontium muthenate material I'm going to talk about today is this structure here. So it's similar to the Cuprates in that it has layers of transition metal oxide planes. So ruthenium dioxide planes here, and they conduct the carriers. It's got a bilayer structure here, so you've got two layers close to each other, and then a bit of a gap, and another bilayer up here. Okay, so and what we're doing here is actually some build on work from Yoshi Maino in Japan and Andy McKenzie and Santiago Gugera, and they did a lot of measurements on strontium muthenate about 15 years ago, and I'm going to show you some of their measurements to motivate the work. So actually, so here you see some recent measurements they've done on the entropy. This is from Dresden. And you can see this peak I mentioned for different temperatures. This is the entropy versus field in strontium muthenate. So in strontium muthenate, as I mentioned, you get this phase, which I'll come to a bit later, and around it we go through what appears to be a field-controlled quantum critical point where we can see this in the entropy. We also get, as you can see here, another property that's associated with many quantum critical points in the heat capacity, which is a T log 1 over T divergence in the heat capacity at low temperatures. And you can see that the critical field where the divergence is biggest in strontium muthenate is around about 7.9 Tesla, this black line here. Here we plotted out the entropy sort of as a contour map, and you can see quite strikingly this sort of V-shaped lines you get pointing to the quantum critical point in strontium muthenate, which actually is about 7.95 Tesla here. And as I said, it's been found there's a phase, so it's not quite a quantum critical point in this case. So that's drawn here. I'll come to that in a minute. Here's the same thing in a cuprate material, actually. So this is an lanthanum strontium copper oxide, the same treatment. You take the heat capacity. So this is some old heat capacity data from John Lawrence in Cambridge, where we've given it the same treatment to show that you also see the signature of some sort of fluctuations here in the overdoped side of the phase diagram. It's a bit controversial whether this is actually just a Van Hoff singularity or a true quantum critical point connected to the pseudogap in this case. But the same sort of physics, general physics implying then we've got some control parameter here, which is the doping pulling us through this point, and some unknown fluctuations in this case. The other thing about strontium muthenate as regards quantum criticality is some of you may be following other systems such as the Cuprates, but not only the Cuprates, where people have seen signatures in the resistivity, a linear resistivity. And when you work out the scattering rate of the quasar particles causing this resistivity, you find in many systems it's approximately given by this equation, which has become the Planckian, known as the Planckian limit, describing this linear resistivity. This is seen in cuprates. beyond optimal doping. And it in strontium muthnate, you see the same thing. Interestingly, if we go right to the field where the quantum critical point is, about 7.9 here, you can see this black line is linear. Again, this is the work of Andy McKenzie and collaborators, and they showed that this linear behavior appears as you approach this quantum critical point. At lower fields, you can see the resistivity is more like a t-squared. Okay, so that was a little bit about strontium muthnate then. So let me tell you a little bit about the ordered phase, and then I'll tell you about the excitations and how we can connect them to the thermal properties. One thing I didn't tell you about strontium muthnate is another of its properties is actually as you go through this special field where we're going to see the ordered phase, there seems to be a change in its magnetic moment, a jump. And ideally, a jump like this would be called a metamagnetic transition, where you apply a field and the moment sort of increases linearly, and then you get a jump here. The moment jumps up, and this is called metamagnetism. And it occurs in many metallic systems, also in localized systems. It actually has some analogies to a liquid gas transition. Here we got field, and if you of course if you have pressure, you have a jump in the density of the system, and moment is of course the density of magnetic moments. So historically, people measure the magnetization of strontium muthnate 327 I'm talking about, and they didn't find that jump as an ideal as the one I showed you, but they see this structure. You can see in the magnetization curve here, it goes up fast here and then slower here. They can see these points where the gradient changes, and if you can then measure the AC susceptibility as a function of field, and these points can be identified as then peaks in the susceptibility. Okay. Interestingly, it's found that when you measure the imaginary part, the outer phase part of the susceptibility, you don't see peaks in the same place in all the places that you see these changes occur. So you can see here the green line is the outer phase part. So that, of course, the outer phase part indicates you've got some sort of phase transition that's got some hysteresis. So a first order phase transition occurring at these points. And this is actually now believed not to be a phase transition. These points then were used to plot out a phase diagram, and that was the first indication that we had something interesting happening in strontium muthnate. And this is the points where you see those peaks in the AC susceptibility, and collected with other data, so heat capacity, resistivity, and NMR. And Andy McKenzie and his collaborators identified this phase boundary here. They also were able to show that if you change the direction of the magnetic field, the resistivity can show some quite interesting behavior. So all I've been telling you so far has had the field along the C direction. If you tilt it away, you can find that you can create a difference in the resistivity along the two in-plane directions here, along A and B. And they call this electron pneumatic behavior. Okay, so at this time, they didn't realize that it was actually an antiferromagnet. So I'll just tell you a bit about that. So a lot of this behavior I've shown you can be understood in terms of antiferromagnetism. The last bit, for example, with the tilting the field, is caused by changing the flipping the moments around, and they can scatter electrons and change the resistivity. So I'd just like to show you our first contribution to this was to show that this phase that had been seen in bulk properties then is actually a spin density wave, and we found that there's actually a second phase here, which we call the B phase. So we saw very easily with neutrons that there were two phases. So what the phases actually are, I've illustrated here, are low magnetic fields. You have an induced moment, and then you have a sort of modulation actually perpendicular to the field direction, like this. And this is the incommensurate order. And then at higher fields, you go back to having your moment like this. So this little twiddle from transverse modulation is the magnetic order you see in this region. So we saw the order using two neutron spectrometers. This is a diffractometer at ISIS, WISH, and this is very good for measuring order. And we actually first saw it on an inelastic machine. This is the LET, also at ISIS, and you can see the very tall detectors here, these 4-meter detector tubes that the LET has, and this is the sample is somewhere here. So this is our original work on finding the order. So we were mapping a reciprocal space here, and we found, looking at zero energy, that we get some scattering here and up here at these incommensurate positions. So this is the origin of reciprocal space here, and then we find these peaks at low temperatures in the region of the field. In the region of this phase. So we see these peaks here, and we found that actually they're resolution limited. So the time we can work out that the spins are fluctuating on timescales, very slow timescales corresponding to less than about 10 micro electron volts. So there's no reason to think they're fluctuating at all, but we can only put a bound on it, of course, by doing these experiments. So you can see that when we go into the phase, we get these. This is the peak here due to the magnetic order, and then when we go a low and higher fields, we see the incoherent scattering that you see with neutrons. So this is constant all over this figure, and then this bit pops up here at these points. So when we had a look at the Q more carefully, we found that actually this is now scanning along this line here to determine what the wave vector of it is. We found that as the field changed, as we changed the field, it actually jumps from one value to another. So this is at 7.8 Tesla, and then there's a region where we see 2 peaks, and then we go to higher fields and it jumps over here. This region with 2 peaks probably means that we have some inhomogeneity, a small inhomogeneity of the field over the sample. So we're seeing both. We don't have any evidence that the two actually coexist. So it jumps from here to here. Anyway, we can measure the 2 positions, and the Bragg intensities at 2 positions at low temperatures, for example, and here's at one of them, and then the other one is like this. And then we can warm up and they go away. So combining all these data, we can add to the phase diagram seen with the bulk probes, the neutron scattering ones, and we find it agrees. We also see, interestingly, if we measure the resistivity, this is this green line, that it kind of tracks the order parameters. You see it has a sort of triangular bit here as a function of field, which corresponds to what we call the B phase. And then when you get into the A phase, it has this structure here, which which follows the order parameter. So the things that were being seen in the bulk properties seem to track the some of them track the ordered moment in the system. So the resistivity that you see seems to track it, suggesting that we're probably creating a gap in states at the Fermi surface, and the resistivity is increasing as that happens. Okay, so here's the phase diagram that's been mapped out with the neutron scattering, and then also bulk probes have then added to what we've seen and so on. So now we've got these two phases, A and B, and the A phase being the strongest one, with the highest TC here. And of course, so the phase corresponds, the difference in these two phases is simply that the Q has just jumped a little bit, which I'll come back to later. So the interesting thing about these phases, the A phase in particular, is these phase boundaries go outwards here, and then they come in. Okay, this region where they go out is where it's found that the phase transition is first order in the susceptibility, in the AC susceptibility. So if you have a first order phase transition, you can use the Clausius-Clapeyron equation, which in undergrad courses is usually derived for the liquid solid, solid or the liquid solid transition, which is first order. So in terms of pressure and so on. But there's a magnetic Clausius-Clapeyron equation, which is this one here. So we can say that this phase boundary here, the gradient dB by dt, so we've got B here and T here, this gradient going from phase 1 to 2. So you can label the phases any way you want. So phase 1 could be the non-ordered phase, and 2 is the ordered phase. Okay, and then you can work out this gradient is given by the change in entropy as you go across the boundary, divided by the change in magnetization as you go across the boundary. So you saw from earlier on that I had a magnetization curve, and magnetization increases. So delta M is positive. This boundary is negative gradient, which that must mean that the entropy must increase as we go into the ordered phase. Okay. And the same must be true actually if we come from the B phase, which also has a gradient going the other way, into the A phase. The entropy must increase, which it sounds a bit counterintuitive that the entropy increases when you go into an ordered phase. But in fact, it happens in many places in nature. And you can see from the free energy equation here that actually you might even expect it always to happen from this equation, because if we want to lower the free energy and we leave U the same, if the entropy increases, we would actually lower the free energy going into the phase. So this entropy, sorry, if the entropy increases going to the phase, it would lower the free energy. So that there's always a contribution that does that, but usually it's outweighed by the change in the internal energy. There's many notable examples where it happens. First was noted by Ossanger in certain liquid gas transitions where the entropy drives the phase transition. But this is a case of that happening in at low temperatures where quantum fluctuations were important. Of course, at the lowest temperature, this line has to actually come in vertical, right? Because there can be no entropy change at the bottom here. So this is a high entropy phase, which I'll come back to later. The other example of this, is skyrmions. Actually, this boundary here if you look at this boundary here, again, this is B dB by dt boundary, and you go into the A phase here at constant temperature, there must be an increase in entropy going into this phase when you go across here. What it means is that somehow the fluctuations that you're inducing are stabilizing the order, and that happens in that case. Okay, so I'll come back later on to measuring the actual fluctuations and show you that we can see the fluctuations increase as we go into the ordered phase. But let me just say a little bit about the origin of the order in strontium muthenate. So why should you get a phase just appearing as you change the field on a metal? Okay, well, we know quite a bit from photo emission about the Fermi surface and the electronic structure of strontium muthenate. So this is some RPES measurements, and you can see it here. So that it's largely known what's happening. This bit's the alpha sheet here is seen in the in here, and also this gamma sheet. But in the corner of this diagram here, up here, something interesting happens, and it's been found from calculations of Efremov and collaborators that that when you change the magnetic field in strontium muthenate, you can create pockets near this M point here, and they appear for certain range of field. And what these people did, actually, they didn't put a field on directly. They forced the system to polarize with these magnetizations here, and they found that for this range, you can see at point 2, you don't see these pockets, and then these pockets have appeared when they have 0.4 Bohr magnetons per rutheniums, and then as you increase the field, they change into another structure. So what we believe is that part of this pocket is flat and is somehow nested to another bit of Fermi surface, and as you change the Fermi surface with the field, then you get enough nesting over a certain range to a field to give you the order. Okay, and you can see this actually corresponds to the system going through a Van Hove singularity as this pocket is created. This hypothesis is supported by the fact that the Qs that we measure actually do seem to change a little bit with field, and that would be the case if it's Fermi surface driven and the Fermi surface is changing. So this is our field-dependent measurements of the two Qs in the two different phases. Okay, so let me say a bit about the excitations now. So we've done the order. Let's have a look at the excitations. So again, back to the motivation, which was to look at the entropy and so on. So here are the excitations measured on the LET spectrometer. So it's the same spectrometer we first saw the order. And if we now make a map of the scattering, the magnetic scattering in the A phase, actually, what we've got here at about 100 milli-K, we can see at 200 microvolts here, 0.2 millivolts, that these peaks are slightly broader in reciprocal space than the elastic peak. And so if we scan across here and then perpendicular, you can see some this data here. So Q parallel is going along this dotted line here, and then Q perpendicular across the peak here. So you see it's broader going this way. And then if we go up in energy, so this would be 0.16 up to 1 milliwatt here, you see these peaks broaden out. So they disperse in energy and they get weaker. So they're not, we don't believe these are propagating excitations, and I'll show you why in a minute. These are diffuse, very heavily damped excitations then that disperse, they broaden in energy, in wave vector as we change the energy. So we can also go to this point here, which is the ordering wave vector, and measure the excitation spectrum. And this is what we get when we do that. So this, I'll flip back to this for a sec. This is done at the field where the phase is strongest, on the quantum critical point in quotation marks, where we see at that field that the excitations are strongest too. So you can see here they're peaked up at very low energies. So just for the neutron scatterers, then of course LET is very good at the measuring the very low energy excitations here. So we're going down to 0.1 EV, and here we've used the multi-rep capability. So these are taken with different EIs, and then we we can normalize the data and put them all on the same scale to get this broad, well, this spectrum. Okay, so this is the excitations we get. There's no sign of any spin waves, right, in this material. So what we seem to be seeing here is the sort of background of fluctuations in the system, and then in this very background of fluctuations, which we're measuring here, we get this very weak ordered phase with a small ordered moment of about 0.1 Bohr magnetons forming. Okay, so you can see that the spectrum changes quite dramatically with field. Then if we go down to 6 Tesla, for example, there's nothing there. Because the temperature that we're measuring at is very low, if we put that into energy units, one can regard most of what we're seeing here actually as quantum fluctuations. In the Bose factor is 1, largely 1. So this is what we're doing here. Then one could say is we are changing the quantum fluctuations in the system with the changing field. Okay, so we've seen that the excitations are very damped. In fact, these lines you see here are damped harmonic oscillator functions. So we can parameterize the whole response that we see as a function of wave vector and energy, actually, in a relatively simple phenomenological cross-section, which we've used. So it's based on a cross-section which is called the Millis-Monian and Pines form, which was used in high-temperature superconductors, and you can write the susceptibility here. So this is the wave vector-dependent susceptibility, which we can measure in neutron scattering. In this form here, this is Millis-Monian and Pines. It was actually also used by Maria in the 1970s to describe nearly antiferromagnetic metals. We can modify this slightly. For each of the peaks that we see, we can use this form, but we've got to make it anisotropic. This is a correlation length here, by having 2 different correlation lengths according to whether little q is perpendicular or parallel to Q delta. So this is called Q delta, this here, and so little q is the distance from Q delta. So we use this as our origin for this this cross section here. Okay, then if we take this thing and convert it to its imaginary bit, which is proportional to what we see with neutron scattering, we get this form here, and then you can sum over the 4 possible Q deltas, so one here, and its friends around the other side. Okay, so this is a way we could parameterize the data. Actually, it doesn't have that many parameters, 1, 2, 3, 4 parameters, the overall intensity, a relaxation rate, and two correlation lengths. So just a little bit about neutron scattering then. Just if we scatter from a sample, we can measure intensity at lots of different points, and we work out the change in wave vector and energy of the excitation. And the intensity, the number of things that we count, is going to be proportional to all of this stuff, form factor, a Bose factor, and the imaginary part of the susceptibility. And what we're saying is that the excitations we see are very strongly overdamped. So this is the response function of a damped harmonic oscillator with different amounts of damping here. If we increase the damping, we go from a sort of sharp peak to this overdamped peak. And what we're seeing is something that's described by this overdamped peak. And that's what is in this. This is actually a damped harmonic oscillator cross-section. You can see there's an omega there, an omega squared here, and this is a constant. Okay, I won't spend too much time on this because there's maybe too much detail, but we can measure the width of the peaks in these scans here, and then and fit them to these different parameters in our cross-section, and this is the fit we get. This is the peak width as a function of energy, and then this is the width along the perpendicular direction, perpendicular to Q and parallel to Q delta, and you can see it all fits very nicely. So we can parameterize the full scattering function with this function here. Okay, and then we can look at things as a function of field. Okay, and in fact, if we want to look at things as a function of field, and you look at the cross-section I gave you, you can get 2 of the parameters just by fitting these points here. So if we go to the peak Q delta, then obviously the cross section, these 2 terms become 0, and we're just left with a damped harmonic oscillator function that depends on the gamma and chi delta. So these plots then give you this. So this is how the susceptibility at the delta position varies with field, and you can see it's peaked up at this point here, and then the relaxation rate is shown in this one. So obviously you can see here that the relaxation rate is smallest at 7.95, and that is here. And then actually you can plot the inverse relaxation rate, which is a time against the susceptibility, and you can see this scaling that you'd expect when you go through a phase transition, a classical phase transition as well. Okay, so as we go through a critical point, in general, you know, like a classical critical point, you expect your physical variables to be controlled by the correlation length, right? And you can get power laws of different physical quantities related to your correlation length. So we're also looking at dynamics here, but the same thing applies. And so Minnesmonian and Pines and other people have shown that for a nearly antiferrometric system, you'd expect these scaling relations with respect to the correlation length in mean field theory. So we can use if we use these scaling relationships, then we can get a model for how the susceptibility varies with field. So the problem with all of this, what we're doing here is it's very expensive to make this map over lots of Qs. Okay, but we have done that for the critical field here. Okay, and we've shown that the function works in that case. But when we go away from it, we can take less data. We can basically get these curves, the energy-dependent curves, and then use the scaling here to infer how the correlation lengths would vary in our cross section. So we can make a model that's consistent with mean field theory. It's also consistent with this scaling that we've observed to work out the field dependence of the scattering. Okay, and what we've done is then to use what's called power magnon theory. So it's an approximation used in metals to work out heat capacity, which goes back to Brinkman and Engelsberg and Martin Donyak and all these people. We can use the cross section to estimate the specific heat. The specific heats that due to basically due to this conduction electrons coupling with the spin fluctuations or scattering from the spin fluctuations. Okay, so this is just to show you what these people have done in the model. They have an expression for the free energy of the system in terms of the spin fluctuations here, and they find that the free energy can be written in this form. And actually, this bit here looks like the response function for one of the modes I've been talking about, and this is the free energy of a harmonic oscillator, which is written here. Once you've got the free energy, you can work out the heat capacity here, and this is the expression they have. Okay, it's hard to get your mind around that, but you can work out, you can evaluate this numerically for a single mode, because this thing here only depends on the gamma, the relaxation rate of that particular mode. And this is the heat capacity you get from that. This is the heat capacity from a single relaxation mode, a single Q. Remember that what we've seen experimentally is that we've shown that the modes that we see are overdamped modes, and then when we change the Q, the damping of the mode changes. And maybe I didn't emphasize that in one of, yeah. So that's in this equation here. So our cross section, we can actually write it in this form here. So this is an overdamped mode, and now the relaxation rate of the mode depends on Q. So it's a very simple thing. So this is just this cross section here rewritten, where this bit here is just going to be the damping rate of the mode squared. Okay, so what we're seeing is that our parameterization gives us a wave vector dependent damping of the modes shown here. We've fitted this to our data, and now in this theory, you can work out the heat capacity for this overdamped mode. Okay, and here's the heat capacity for this overdamped mode. Now, if you're in a situation where the temperature is much less than the damping, so kBT is much less than h cross omega here, you're down here on the curve. Edwards and Longzowicz noted that this actually is a constant, and the heat capacity of a single mode is given by this thing here. Okay, so you can see that the contribution of a single mode to the heat capacity depends on this gamma. So the heat capacity that we're talking about, the best way to write it is actually like this. So the heat capacity of a temperature, because in a metal, of course, you can have the electronic heat capacity at low temperatures will be linear, and this is what this will be. So this is the sort of shape that we saw in the heat capacity of strontium withenate. It goes up, and then it would sort of plateau like this if it weren't for the order. Well, it did actually plateau like this. Right, so the very useful thing that Edwards and Longzowicz came up with is this formula then for calculating the heat capacity, the low temperature heat capacity of the spin fluctuations in a metal. So this is the thing you need to take away, actually, just this formula. So if you can measure the relaxation rate of your modes, spin fluctuation modes, okay, as a function of Q, okay, and then average this over the Brillouin zone, over the relevant modes, and multiply by this factor, one should estimate the heat capacity of your spin due to your spin fluctuations. There's a factor mu here, which is how many modes you're concerned with, how many polarizations of modes. So if it's a power magnet, there'd be 3 modes, for example. But we just leave it as mu for the time being. So this is a very simple expression for the low temperature specific heat here. Okay, well, now we know this from our data, we can put this in to get the gamma. The question is actually, what do we put for mu here? How many modes do we have in strontium withenate? Well, interestingly, it seems we only have one mode. One mode. All this scattering I've shown you is coming from, amazingly, is coming from one mode, one polarization that's gone soft. And we can see that by measuring with neutron scattering around, instead of around the origin, which is where we measure with LET, if we go and measure around the reciprocal lattice point here, we can see how many modes are contributing. And that's because of a famous fact with neutron scattering, that magnetic neutron scattering measures fluctuations perpendicular to the wave vector transfer of the neutron. So this big Q is the wave vector transfer, the neutron. So if we go to this point here, we'll only see fluctuations perpendicular to that. Okay. So here's our propagation vector, the little q of the excitation. And at this point here, there's 2 possible propagation vectors. We could go along here, or we could go along here. So they should be, the excitation should be the same. So if it goes along here and oscillates this way, or along here, it might go this way, or if it goes along here, it oscillates longitudinally, and then along here longitudinally. You can see in this data here, actually, that if we go to this point here, we see that point would be actually this point here. We've got the wrong point there, 0.77. Go here, but the same thing still apply. Here we see some scattering. If we change the field and go through the interesting region, you see an increase in scattering here at 0.3 millivolts. These are the fluctuations I've been talking about. If we go to this point here, it doesn't change. This would be so we can use this sort of selection rule from neutron scattering to say, in fact, that when we go this way, the excitations must be transversely polarized this way. So there's only one mode to go in this equation. Okay, so then what we've finally, just finishing up then, what we've done then is to use this formula to connect the spin fluctuations to the specific heat of the material. So, and the specific heat being the specific heat divided by T, because it's linear, and that should be sort of fairly constant at low temperatures. So it's just the value it heads towards. And this is the measured specific heat here. This line measured by Rost et al. And then we've obviously only measured a few fields with our neutron scattering. So these points here are the fields we've measured. And then we can use our parameterization of the scattering function and work out this average of the relaxation rate, inverse relaxation rate, and these factors. And this is the, you can see that it matches fairly well with specific heat. Of course, we wouldn't expect a perfect match in something like this, but it has the right ballpark, and it increases as we go into the ordered phases. This point here is clearly higher than the green one, and both in our model and the measured. And we expect this because the spin fluctuations are softer in the ordered phase, as you saw from the data. So the gammas would be smaller, and that would increase the specific heat. We can also plot all these different points on the line, so we can think of these are different fields, showing that the scaling of this formula works for different fields. And we've also estimated some other materials with spin fluctuations using the same model. Here's the 3 to 7, for example, and then we've got heavy fermion there, and Marcus Braden and Igor Mazin have done a similar thing for strontium 214 here, and it shows that this type of picture seems to broadly explain the specific heat of a wide range of materials. Strontium muthenate is unique in that on this curve, in that the other materials, the mu here has been set to 3 if they're paramagnetic materials, but putting the field on strontium muthenate creates this unique mode that's very soft and gives it its relatively large specific heat. You can read about this on the archive, and this earlier paper here is for the other materials. Okay, so finally, what have we learned in all of this? So the spin density wave is occurring in a background of strong spin fluctuations. We can sort of account for there's a large entropy anomaly in the region of the spin density wave. This thing here seems to correlate with our spin fluctuations and with our model. Spin density wave is easily seen through transport and anisotropies it induces. So what we've been talking about the last bit, the more recent stuff then, is the quantum fluctuations, quantum spin fluctuations. And on entering the spin density wave state, these become stronger, suggesting that the spin density wave may be stabilized by the fluctuations. As I said before, there are other materials where this happens, and it's generally called an order by disorder mechanism. And the general reason is that the system can explore, more configurations and lower its quotation marks kinetic energy by doing this. So that seems to be part of what's happening in strontium muthenate although the underlying thing we think is the Fermi surface changing with field. We can understand electron-specific heat in terms of spin fluctuations. And I should say that there are other systems that are related to this. So, for example, chromium, where you have also nesting, and uranium, ruthenium-2, silicon-2, which has also a field-induced spin density wave. And this other material shows some field-induced effects as well. Okay, so with that, I'll thank you for your attention. And
thank you very much, Stephen. Yeah, fantastic talk. Yeah, so there are quite a few questions. Maybe who wants to ask first? I guess during the talk, Bob Kava asked you, whether the system is actually orthorhombic. He asked me what is the orthorhombicity. I thought it was orthorhombic, right, based on my reading of your earlier papers.
That's a good question. I think there may be some orthorhombic distortions because of the octahedra, small octahedra rotations and so on. But for the level of what we're doing here, we've treated it as being tetragonal.
I see. So do you know the size of the orthorhombicity of the system in the field-induced orthorhombicity within the dome?
I don't know of evidence for field-induced orthorhombicity, but the actual structure, there's some structural papers that say it may not be the very simple structure that I've drawn, but I think for what it has an unusual structure in any case, right? With the octahedra rotate opposite ways in the planes. So strictly, it's not a tetragonal system, but it has a fourfold axis.
I see. So Chandra, you have a question?
Yes. Hi, Steve.
Hi, Chandra.
To study quantum critical properties, one usually has to study as temperature goes down with your control parameter B, in this case, close to B sub C. I didn't see much data with that regard, in which you're studying what you call the damping rate as a function of temperature, or the correlation lengths as a function of temperature. Is that correct? You didn't study that?
I didn't talk about it. We have studied it. We have had a look, yeah, but that's kind of work in progress.
Because without studying that, you cannot get information about the T log T, a specific heat, or about the linear in T resistivity.
Yes, I totally agree. And those are very interesting things to do. So what we've done is to measure at a small but finite temperature as a function of field.
Yeah, okay. You're probably aware of a paper by Mustakas, Berg, and Hartnell on this system, where they have studied quantum critical properties theoretically as I defined it. Are you aware of this paper?
Yes, about the hotspots, you mean?
Yeah, well, I wanted to see whether the fluctuations that you study, if you studied it as a function of temperature, whether they had omega over T scaling as comes out in that theory, which would be necessary to get your T log T specific heat and the linear in T resistivity. So that would be an interesting thing to explore experimentally.
Absolutely, Chandra. No, I'm totally agreeable. Yeah.
Thank
we
you.
have done, well, I can tell you that it does show some scaling, but we're working on it at the moment, yeah. But it's really a question of how high in temperature you can go in this material, because it has some changes. For, you know, there's a temperature scale, another temperature scale in there, isn't there, where it the susceptibility, I think, has a peak at about 20 K. I have to refresh my mind, but yeah, it'd be very interesting to do the temperature dependence. Totally, I agree with you. But each experiment takes a long, long time. That's the problem with it.
Yeah. Okay. So Qimiao, do you
Yeah. Hi, Stephen. Nice.
Hi, Jim.
I have two quick questions. So the first one is probably related to what Chandra was asking. You know, the scaling properties and even your fit to the entropy would strongly depend on the dimensionality of the quantum fluctuations. And I wonder whether you have the information based on the Q parallel and the Q perp dependence in near BC about whether the fluctuations is 3-dimensional or 2-dimensional.
Yeah, I think I skipped over that because there was a lot of so the fluctuations are 2-dimensional, as you can see here. So this is at 0.2 millivolts. Yeah. So these are the fluctuations at the increments of the characteristic wave vector, measured as a function of L, and you can see it's pretty flat. And this is the order, the blue points, which shows the order is 3-dimensional, and the fluctuations are 2-dimensional.
I see.
So
does that answer your question?
yeah, no, that's very interesting. That helps with the, presumably that's what you use in the in connecting the susceptibility, the dynamical susceptibility with the entropy.
Yes. So these formulas here are all 2-dimensional.
Okay.
Because I've only got, so these two correlation lengths are both in plane. So one is along here, and one is along here.
And I have, if I may, could I ask a follow-up on this entropy thing? One of the things I recall for this system is that there's a lot of entropy in the quantum critical regime, something like 10% of R log 2, if I remember correctly, and the gamma, the specificity coefficient, is enhanced quite a bit.
Yeah,
I don't remember, like 100 millijoule per per mole Kelvin square, something.
Yeah, this is the gamma here. Yeah, so it's
right.
It goes from 100 to
and I wonder whether in your analysis you have assumed some sort of background mass enhancement.
No. So, well, this is where our analysis, this analysis, and my understanding of this analysis is this gets you the heat capacity from a different route than thinking about it in terms of electron quasi-particles. This is just putting the entropy into the spin fluctuations as a sort of another way of getting the heat capacity. So there's no background thing here. if you want to apply, I mean, one could apply this approach to, to sodium, where gamma would be very big, right? And would still get some heat capacity, which I assume would be, what you would get from a close to what you get from a free electron metal or something. But I'm not good enough theorist to do that. But it's another way of getting the heat capacity.
Yeah. So he can do that because Stephen measured the scattering in absolute intensity.
No, I understand the procedure. I was slightly surprised by purely long wavelength fluctuations giving rise to so much entropy in the quantum critical fluctions. But I'll look at your analysis in some detail. Thank you.
Okay, I'll be interested in anything you have to say about it. So please ask me more questions when you've had a look.
Thank you.
Yeah, please, unmute your mic, Ross.
So beautiful work. And I think I would like to know, is this averaging over, if the material is actually orthorhombic, sorry, it's a crystallographic question. How big are the domains? Is the quantum critical behavior averaging over small orthorhombic domains, or what?
Yeah, the correlation. So the longest correlation lengths we see are here. So if you take the inverse of those, that would be the size which we're averaging over.
Thank
you. I guess that's
big.
That's
ish.
It's not that big, actually, is it?
Not so big, yeah.
No, it's going to be within the domains.
Right. Thank you.
Yeah. So Ross McDonald, you have a question?
I don't think he has a mic.
You don't have a mic. I'm sorry.
I can read his question from the chat if you would like.
Oh.
Okay, please. Yeah.
Yeah. So he has a two-part question. The first part is the increase in entropy in the A phase. Does that depend on the magnetic field if you rotate it away from the C axis? And if you follow up on that, could some of the entropy of the incommensurate A phase be the orientation of the transverse moment, which presumably could be suppressed with a component of in-plane field?
If the maybe if I can find the chat, I can.
You can read yourself.
I don't know. Yeah, Ross. Increasing entropy in the A phase, is this still the case if you wrote away from B? Well, I think that's a good question. I've no reason to think it's otherwise, but if you rotate away from the C-axis, then the region of the A phase gets smaller. And I don't think people have done detailed measurements to see what the gradient of the boundaries are. Mm-hmm. But there's no reason to think that that wouldn't still happen. But I don't think there aren't any measurements. A neutron scattering, we do have some measurements rotated, but not as a function of field, just at the field where the phase is. Okay, that's that question. Are there any more that?
Oh, hey, Steve, it's Ross. I've invaded Joanna's office so that I could get through to you. Thank you for answering that. My logic in asking that question was pertaining to the slide you showed with the pneumaticity and the resistivity, where as you tip the field into plane, you're clearly breaking that symmetry, and whether or not that connected to the to reducing a degree of freedom that was actually some of this entropy that's associated with the A phase. So I think you answered the question, but I think there's potential there to use your Clausius-Clapeyron relation with tipped field to see if you change the entropy of A as you tip the field.
Yeah, I think Ross, I can answer your question. So I now understand what's behind your question. I can tell you I can perhaps answer another question which might you. So we have measured we've measured the order and the excitations in tilted fields. Yeah. And we find that basically, I don't think I showed it in this talk, but maybe let me just see. It was hiding there. Yeah, I don't think I showed it in this talk, but I can show you. So you can see can you see the two peaks here? If we tilt the field along A, for example, which in our original paper, what you see is that only one of these peaks remains. It just, and so we understand the resistivity by the spin density wave causing a scattering. The excitations don't change very much when we tilt the field, only the order.
Okay, so that was actually part of my question, was whether fluctuations between those two orders were part of the entropy, or they're static with some domain structure, and then you have separate fluctuations. I guess that's another way of asking my question.
Okay, there's quite a bit of sort of controversy in the literature about domains. There are no domains because in spin density waves, if Chandra probably knows more about this than me, but in spin density waves, you get a modulation along a direction, and then the other, it doesn't interact with the one along another direction. So you can wipe out one of these peaks and the other one hardly changes. And that's also seen in other systems. So there are no domains. And I think that, I know Andy Mackenzie talked about domains, but his recent work with Cliff, where they put pressure on, I think is also inconsistent with domains. So there's not any domain scattering causing in the resistivity. Spin density domains we're talking about, right?
Yes. Okay. Thank you. No, that's an interesting case then. Okay. Thank you.
Yeah. So Stephen, let me ask you. I mean, so the Rossini has known to be a very strong, spin-orbit coupling. So I mean, is the spin fluctuations in this regime really sort of a completely anisotropic, or have you done polarized measurement to show? I mean, you said it's a sort of a damped paramagnetic scattering, right? So what is the polarization, of these paramagnetic spin excitations?
There's a lot of evidence that spin-orbit coupling is important. For example, if you put the field in plane, then this phase is shifted several Tesla in field. So the spin orbit is important there. And I suspect, it seems to me that any theory that gives you the polarization of the ordered state needs some spin orbit in as well. And there are many papers on spin orbit coupling, but I think this is before the spin density wave was seen. So I think spin orbit coupling definitely important. We don't need to do polarization analysis to see what the polarization of the ordered state is, just because we only see,
one state, right? Basically,
one polarization, yeah.
Okay. I mean, Hayang.
Hi, Stephen. Thank you. That's a very nice talk. I have one question about the connection to the 214 single layer case, where early days we have seen the incommensurate inelastic peaks in the 2 and 4 as well, above the superconducting transition temperature. Can you make some comment to the 3 to 7 versus 2 and 4, especially related to your spin fluctuations?
Yeah, that's a good question.
Tough question for him. Yeah.
I think in the 214, the incommensurate peaks come from a sort of nesting, which is there at a zero field. And I believe that the band structure calculations get you those nesting vectors in the 214. The 3 to 7 calculations from Eremov require that the octahedra have to tilt to give you these pockets. So you have this funny structure where they tilt in opposite directions in the neighboring planes. And that is essential in the band structure to get this these pockets that we now believe cause the nesting. So you need the field and those tilts. In the 214, you get these, you get weaker peaks, obviously, because it doesn't order in the pure strontium euthanate. That's probably all I can say.
I mean, can I, sort of, get the conclusion from the, because the 2 and 4, when you're talking about nesting, it's coming from the 1D orbitals. It's an XC1Z orbitals. While the pocket that you're talking about is gamma pockets mainly made of the XY orbitals.
Yeah.
So probably one has to know some details about orbital composition in the Fermi surface to understand the difference between the 2 and 4 and 3 to 7. And that's where the spin-orbit coupling comes in, right? Because they all mixed up by the spin-orbit coupling as well. So I'm trying to understand if one has to understand this, if you want to know the microscopics, then probably one has to know the orbital compositions and how they couples each other and how they differ between 2 and 4 and 3 to 7. Is that the right direction to think about?
I think so. I think what you need to do is just, I'd say to do a proper model of the 327 with orbital character, just the normal orbital character in there first. As you say, I don't know how that would affect how that would affect the susceptibility, which bands would have the right matrix elements and so on. But as you say, the spin-orbit coupling is important. Even in the 214, I think, are some calculations which, in order to get the sort of anisotropy of the spin susceptibility which has been seen, you need spin-orbit coupling to be in there. But I don't think anybody's really done a sort of model that gets you the susceptibility in the 327 with these pockets yet. They've just calculated the pockets. So that would be really good to do if you could do that.
Okay, you just reassign the work back to you.
Thank you.
Thank you. Yeah. All right. So if there's no more questions, it's quite late for Stephen already. Yeah. So we really appreciate this very much, Stephen. Yeah. Thanks, everyone. Yeah.
Okay.
Yeah, thank you.
Thanks. Bye. Thank you all. Bye.
Thank you, Stephen. Yeah. Bye.
Bye then.